Hi everyone. So in this video, we are going to prove the pinching lemma that, as we saw, will be one ingredient in the proof of the R transform and will allow us to do the interaction. Okay, so if you want to have a quick look at the lemma, here it is, kind of with many red lines and remarks, but it's like at first 2/3 and or half, and and you can be impressed from from its length and so many things we actually want to establish here. The proof actually is quite simple, nothing fancy. So the first thing we'll do is we are going to define T as the max root of U alpha P. Right? If you remember in the proof, what you want to prove in the first place is that the max root of U alpha P, which is the main player in this act, is shared with the max root of U alpha P hat and P tilde. And if you recall, P tilde and P hat are going to be kind of variants of P. We are going to replace lambda 1 and lambda k as roots when constructing P tilde and P hat from P. And in P tilde, we want to add mu as a double root. And in P hat, we want to add a rho as a root. And one root only, so the degree will decrease by 1. And actually, the kind of construction or definition of mu is like very explicit and rho also, but let's start with mu. And let's define it as follows. So if T is the max root of U alpha P, and of course recall you gave me alpha and you gave me P. So now I know T. When I'm going to define mu like that, like this equation, it's T minus something that look like something that resembles an harmonic average, and it is actually. So the best way to read this definition of mu is actually not to define mu, but derive it from this equation. And here you see we defined T minus mu as the harmonic average of T minus lambda and T minus lambda 1 and T minus lambda k. Okay? So it's the same thing, but this is the explicit definition of mu, and this is kind of the real reason we want to define mu like that, as we'll see in a second. And the harmonic, so as a remark, T is larger than lambda 1, right? Because T is the max root of this thing, and lambda 1 is the max root of P. And if you remember, so the K transform of them, or the max root of U alpha P, it's always an upper bound for any alpha larger than 0. It's always an upper bound on lambda 1, right? Because it's the pre-image of something, of say alpha, or well, maybe alpha D or alpha over D, whatever, some parameter depending on alpha, in the last branch, which is to the right of lambda 1. So by definition, T is larger than lambda 1, and therefore this is positive, and lambda 1 is strictly larger than lambda k, so also this is positive. Okay? And why do we define T minus mu like that? Well, let's look at the Cauchy transform, or this is more precisely the unnormalized Cauchy transform without the 1 over D of P tilde. Right, so in order to compute that, what I should do is you go over root by root and look at 1 minus, so here I'm evaluating a T. So 1 over T minus the corresponding root. And the roots, what are the roots? So by definition of P tilde, we have a mu with multiplicity 2. So you will get twice 1 over T minus mu. And then these are the roots that are common to P and P tilde, right? Now, the reason we defined mu like that, or 2 over T minus mu like that, is precisely so that this equality will hold. Namely, 2 over T minus mu is precisely what appeared as the two summands that do not appear here when you look at dP over P evaluated at T, right? Because this is precisely that plus these two things. And so we defined it in such a way so that we'll be sure that at T, the normalized and also unnormalized Cauchy transform are the same for P and P tilde, which doesn't quite prove that these two are equal, but almost, right? We know now that T is a root of U alpha P tilde. We want to show it's the max root. But let's do it slowly. And this is the slowly part. So just as a reminder, saying this thing, saying that the Cauchy transform of P at X is W, is the same thing as that. That was just a little bit of moving things around, which is the same thing as saying that by definition of U of the operator U. So in particular, if we know that T, and we know because that's how we define it, is the max root of U alpha P, then it's the same thing as saying that T is the maximum X for which this equality holds. And kind of unnormalizing the Cauchy transform, it's the same thing as saying that T is the maximum X for which the unnormalized Cauchy transform, right? P prime over P is 1 over alpha, right? Because these two are related by a factor of little d. So what I'm saying is that the equality that we just proved in the previous sheet, namely that dp tilde over p tilde is the same as dp over p, evaluated at t, is 1 over alpha, right? Because of that. So as I was saying before, t is one of the roots of u alpha p tilde, and what we want to show it's indeed the max root of u alpha p tilde, and that will establish like half of the first equality, or a third, depending how you. But it's transitive, right? You prove 2, you prove 3. So okay. So let's see why it's true. So just kind of as a reminder, this is dp over p. So it's these two things plus the common part, g of x, which is just the sum of 1 over x minus lambda I when you exclude I equals 1 in k. And dp tilde of x over p tilde of x is the same thing. You have the same common thing, but you have this 2 over x minus mu other than these two summons, which recall at t are equal, but generally are not. Now, and we want to show that t is the max root of u alpha p tilde. So first of all, t minus mu is the harmonic mean of t minus lambda 1, t minus lambda k. And these two numbers are distinct because we assume that lambda 1 and lambda k are distinct. And in such case, like basic inequalities or average inequalities, mean inequalities, you know that t minus mu is in between, but strictly in between t minus lambda 1 and t minus lambda k being the harmonic average, harmonic mean. Okay? And so mu is between lambda k and lambda 1, not to be switched the directions, but strictly in between those. Okay, so actually that also implies 2. So we are trying to actually prove this equality, but on the way we just prove this thing, right? That mu is between lambda 1 and lambda k. So that's done, but we need it as we go on. Now, what I'm saying is that the max root of p tilde is at most lambda 1, right? Because you only added a mu. Actually, it's you only added mu to it, right? So if you look at p tilde, where is p tilde? It's kind of a mess here. But p tilde is this polynomial. You added mu, and you removed one instance of lambda 1 and one instance of lambda k. So the largest max root of p tilde is at most lambda 1 still. There could be other lambda 1s, right? So at most lambda 1 still, and if there are no other lambda 1s, it's going to be mu, because lambda k is the next competitor. But, it's at most lambda 1 nonetheless, right? Because you only added mu, which is smaller than lambda 1, and you remove the lambda 1, and you remove lambda k. And so this means that this function, like the Cauchy transform essentially, is strictly monotone decreasing in lambda 1 infinity, right? Because, so maybe we should have a picture to better illustrate that. So I'm looking at p tilde, gp tilde, okay? The Cauchy transform of p tilde. Normalized or not, it's not really interesting at this point because I care about whether you are strictly decreasing or not. So and I care about the roots, so it doesn't matter. So GP tilde, um, the last, so sorry, 1 second. Let me just be sure that I'm saying the right thing. So we claim that the max root of P tilde is at most lambda 1. And so I don't know, it could be, it could be mu or lambda 1, but it's at most lambda 1. And so because of that, so the last pole of the corresponding Cauchy transform is at most lambda 1. It's either lambda 1 or mu, but it's at most lambda 1. And from that pole to the right, you're strictly decreasing, right? So that's the picture here. So you see the blue line, the blue branch here. Well, I'm drawing in red, but the blue branch here is strictly decreasing from lambda 1 or mu downwards. And the point is that T is larger than lambda 1, right? We just said that before, that because lambda 1 is the max root of P, uh, T, which is a max inverse of this corresponding Cauchy transform, is always to the right of lambda 1. So T is to the right of lambda 1, in particular to the right of mu. And so we know that this function, or its unnormalized version, but it's the same, has a 0 at T. And we know that already from lambda 1 or from mu, which is before T, the function is strictly decreasing. So in particular, if it's attained some value at T, it's not going to attain it again, right? It's attained the value 1 over alpha at T. And so in excess to the right of T, it's definitely going to be smaller. And so it's not going to be 1 over alpha, which implies that indeed T is the max root of U alpha P tilde. Okay. So essentially, once you're to the right of the max root of P, you know that in the Cauchy transform mode, you are strictly decreasing, right? Because roots of P corresponds to poles of Cauchy transforms. Good. So I think we're done with P tildes. Like anything we want to say about P tilde, because what did we want to say? We kind of defined it explicitly. Once I gave mu, I defined it explicitly. And we just proved that the max root of U alpha P tilde is the max root of U alpha P. And mu, which is the new root of U alpha, of P tilde, we just bounded by lambda 1 and lambda k, just because, T minus U was the harmonic average, and therefore mu was, and lambda 1 is different than lambda k, so mu is strictly sandwiched in between these two numbers. So let's move to P hat, right? So moving on to P hat. So let's see. So P hat by definition is just the difference of these two things. We were given P and we defined P tilde explicitly. Namely, I told you what mu is. So now let's kind of infer what rho is, okay? So just, subtracting these two polynomials, this part is common to both. And this is not, right? So P has this factor and P tilde has this factor, right? Mu appears twice, and in P you have lambda 1 and lambda k each. And if you open this up, you see the x squared gets canceled, right? And the coefficient of x is this number here, 2 mu minus lambda 1 plus lambda k in brackets. And then there's this thing. And so first of all, what I claim is that, okay, we already see that this is a degree, well, at most d minus 1 polynomial. Potentially, this could be 0. But what I claim is it's not 0 and it's not negative, it's positive. And we want it to be positive because PD minus 1, to stay with the induction, PD minus 1 requires a positive leading coefficient. And the reason that this is indeed positive is that, well, T minus mu is the harmonic mean of T minus lambda 1, T minus lambda k by definition. And the harmonic mean is always bounded, and actually strictly bounded when the individual terms are different, than the average mean, okay, like the usual mean. namely t minus lambda 1 plus t minus lambda k over 2, the arithmetic mean, sorry. And so from here you can see just, you have a t here and you have a t here. So you can see from here that mu is at most lambda 1 plus lambda k over 2, which gives you that this coefficient is indeed strictly positive. So indeed, p hat is a polynomial of degree d minus 1 with a positive leading coefficient. It's not a monic, but it's positive leading coefficient. Okay, so that's one. What else do we want to prove? We want to prove that its max root is the max root of u alpha p hat is the same as the max root of u alpha p, and what we already know now is the same as the max root of u alpha p tilde. And okay, so first of all, indeed, at t, you get a zero, right? U alpha p hat, because u alpha is a linear operator. It's the u alpha p t, evaluated at t minus u alpha p tilde evaluated at t. And we already proved these two are the same, so you get a zero. So this means that t is indeed a root of this polynomial u alpha p hat, but we want to prove it's a max root, right? And we are going to do the same thing. In order to prove that, we are just going to show that the max root of p hat is at most t. Right, because, or strictly smaller than t, because that means that, uh, from the max root of p hat, we know that the Cauchy transform decreases, strictly decreases. So you can't have another root of this thing to the right of t, right, because of the relation of the Cauchy transform in u alpha p. So again, I just want to prove that the max root of p hat is at most t, like we did for the p tilde, same strategy. But this is kind of more annoying computationally. So we want to prove that p hat has no root, after t. Now t is after lambda 1. It's larger than lambda 1. So the only root that could kind of spoil the party is the new root rho, right? Because all other roots of p hat are common to the roots of p. All of them are at most lambda 1. T is strictly larger than lambda 1. So the only problematic root is potentially rho. So we need to make sure that also rho is not larger than t. And what is rho? Well, rho is this thing, right? I mean, sorry for going back and forth, but when we actually wrote down p hat, you see you had this term and that term. And when we simplified it, you see that the rho is actually this divided by that. Right? So it's this thing. And now if you're going to plug the definition of t and play with it a little bit, you can show that t minus rho, it actually takes some time, I think, or at least the way I did it. So t minus rho is this expression that you have here. Okay, so that's rho, that's t. You look at the difference, you kind of clean it a little bit, and you get this expression. And this expression is indeed positive because we know that mu is between lambda 1 and lambda k. So both of these are positive. And we also know that the denominator, t mu minus the sum, is positive because we just proved that before here, when we proved that this is indeed in PD minus 1, a positive leading coefficient. So you have a ratio of, a ratio of positive numbers, it's positive, strictly positive. So this means that t is at least rho, which is what we wanted. Okay, so to conclude the proof of the pinching lemma, we just have to prove this little thing about rho, item 3, I think, here. It's the only thing that's missing. I mean, we just proved that now. So the only thing that's missing is proving item 3, namely that rho is at least lambda 1. Okay, the in particular part is obvious, and we said that. And that's actually a little trick, if you want to do it quickly. So let's look at this expression. Okay, so this expression involves what you want to prove is larger than 0, because proving that this is larger than 0, strictly larger, is proving that rho is strictly larger than lambda 1. But we know that this other term that we have here is at least 0 because larger than 0 because of what we said twice already. Uh, but this expression is nice because when you open it up and use the definition of O, that's easy. You get this thing, which you can complement to a square. So you get mu minus lambda 1 squared. And this is strictly larger than 0. It's obviously at least 0, but it's strictly larger because we know by item 2 that mu is between lambda 1 and lambda k strictly. So anyhow, this is indeed strictly larger than 0. And we know that this is strictly larger than 0. So this means that rho is strictly larger than lambda 1. Okay, so that was the proof of the pinching lemma. We need some more preliminary lemmas about polynomials in order to conclude. Just to give you the picture, I told you it's kind of long. We are kind of here, so we want to prove this theorem, and we just prove the pinching lemma. Okay, so the next thing we're going to do is to prove a couple of little lemmas, maybe the literally little lemma, and then lemma A. That's a significant lemma. It's interesting. It's like more interesting than the pinching lemma. It has something non-trivial to it, and we'll continue from there. But just so that you will have some, proof strategy in mind.